For today's lecture, there's a decent amount of slack time in here. It's probably like a 45-minute lecture or so. If you have questions, feel free to jump in. Feel free to ask me as I'm going through this. And I'll pause a few times to make sure we get all the questions out there. We're going to dive into a more complex example of the state pattern, which will obviously help for the current homework assignments and the lecture questions this week. So if you have questions, please air them out, let me know. Let's talk about them. So we're going to be talking about the jumper game. For those of you who did rhyming dictionary, or if you weren't able to finish the jumper game and get the full experience of what this is, I just want to show it off and show you what we're talking about in general. So this is the game. I can move around, jump on these platforms, and this is a 2D vertical scrolling platformer. So right there, I just won the game. The blue player fell off the edge of the screen, the bottom of the screen. It means that player's done, and I won. So the goal is to jump higher than the other player, jump higher faster than the other player, get the other player to hit the edge of the screen. So, and we've talked about a few things like with this. We'll revisit the physics of this game. I land on these platforms, but I can move up through them, and I can't go through these walls. That wall is blocking me from moving over. Which we'll revisit just quickly. But we also have a fairly complex jump mechanic, and that's what we want to talk about today. We use the state pattern to get this jump mechanic, and we're going to see how to implement that. So the features of this is if I'm standing and I jump at a particular height, and I'm holding down the button when I'm jumping here. If I move and jump, I have a higher jump if I'm walking while I jump. And also, for that, I was holding down the button too. If I just tap the button, I'll have a smaller jump as well. And if I hold the button down for a little bit longer, I can get a higher jump depending on how long I hold down that button. So if I want to run and jump and do little hops, I can do that. If I turn around mid-air, I'm going to have a slower speed after I turn around. And if I walk off a platform, I'm going to fall, of course. And a few other things. We'll look at the full feature set when we get to the slides. So if you didn't finish this assignment, or if you did Keynote, or if you did the rhyming dictionary, I recommend go through the code. If you haven't already, I recommend this on Monday too. But go through that code, go to the physics engine, clone the starter repo, and take a look at how we do the state pattern. All the code we'll see today, it's in that repo. It's all built into that. So take a look at all the states, play around with it, break it, add new features, get a good feel for how this stuff works through that. So the lecture question today is going to be another state question. No control flow, same rules as the homework. You can expect the same thing on Friday. We're just getting more complex feature sets each time. So we're going to get a nice and good practice leading up to these homeworks. And of course the homework assignments are the big state pattern assignments to be able to apply this. But we're building up. We had a fairly simple, straightforward one on Monday. Now we want some more complex behavior. How are we going to implement this behavior? So what we want to build here is a TV class, capital T, capital V. Don't do the lowercase v. It's a frustrating mistake. TV class with these 5 methods in its API: volume up, volume down, mute, power, and current volume. And we want all of this behavior based on this API. We want all these different pieces of functionality in each of these bullet points as we're building this TV, and a test package, a test suite, test TV, which is going to test all of this functionality. And just a reminder, this is always the case, but ever prevalent now. You're going to be writing a lot of classes, a lot of methods that are not defined here. You have a lot of some state variables that aren't defined here. Just make sure you're only creating TVs in your testing, and you're only calling those 5 methods of the TV class in your testing. So we'll get to start seeing the other side of the state pattern of how do we use something that uses the state pattern. Well, you don't care that it's using the state pattern. You just create a new TV, hit the buttons on the remote, and ask for its current volume. That's all you can ask for. So you're most likely going to have some variable in your TV class, some state variable storing the current volume, the volume of the TV. You can't access that in your testing because you have no guarantee that I'm going to have the same variable with the same functionality. But you can call current volume. That's your one access point to be able to test this thing Mash a bunch of buttons, call current volume, mash some more buttons, call current volume. Make sure current volume is always returning what you expect to be returned. Now you can write more tests in a different test suite. You can create another one that tests your specific functionality, your specific implementation. But when you submit and everything in test TV, you can submit with that other test suite too. But everything in test TV has to follow only these 5 API methods and only the TV class. Just a heads up with that. It's always true, but more prevalent here. You're going to be more tempted to test your specific implementation in this one, just from the past. That's what people do. So some of the functionality, I won't go through all this, but some of the functionality here, when you first create a new TV, it should be in an off state, and its current volume should always return 0, but the volume of the TV is actually initially 5. So the current volume is the current volume that a user is experiencing from the TV. So the user is currently experiencing 0, but once the TV is initially turned on with the power button, the TV is going to return a volume of 5, and it's going to have an internal volume of 5, and the volume up, volume down buttons are going to do what we expect, increasing and decreasing the volume by 1, up to a max of 10 and a min of 0. When the TV is muted or turned off, the current volume is going to start returning 0, but when it's unmuted or turned on again, it should pick up with whatever volume it was. So if I turn on the TV, hit up twice, get a volume of 7, turn off the TV, current volume should return 0, but the TV should remember that 7. So when I turn it back on and call current volume, that should be returning 7 again. Same with muting. If I turn the TV on down a few times, I decrease the volume to 3, and then I mute the TV, current volume will be returning 0. And then if I push mute again, it'll unmute, or if I push volume up, volume down, it's going to unmute without changing the volume. So if I hit any of those 3 buttons that all have the same functionality, that'll return the volume to 3. It'll give me that current volume again. It's not going to reset. So the initial volume is 5, but that's only for when the TV is first created. After that, it should always revert back to what it was. So create a new TV and turn it on, the volume's 5. Change the volume, turn it off, and turn it back on. It should revert to whatever it was when you turned it off. Any questions on the question itself? Okay, let's talk about jumper. So we talked about what the game is, what our goal is, our 2D vertical scrolling platformer where you gotta jump faster than the other player. Let's start talking about how we built the functionality. We talked about physics engine already, how we used inheritance and polymorphism to get the functionality with our physics engine. And when you wrote your, so we extended static object from platform and walls, dynamic object from players, and when you finished your physics engine, it just worked with the game through polymorphism. So you had, when you run the game, there are platforms and walls in your static objects list inside that world object. And then when you call update world, it's working with platforms, walls, players. But in your physics engine itself, you just care about dynamic and static objects. You don't care what they actually are. Now at this point, we care what they actually are, and then we're going to throw them into a game world, give that to our physics engine, say, hey, update this world every frame, and that's going to give us the functionality. So that physics engine, the game you just saw, that my physics engine class, that just follows the spec of the homework. I don't have anything extra in there to run this game. And if you did finish that homework, you can run this game, run the GUI, and you're playing the full game with all the features with your physics engine by because we leveraged that polymorphism to be able to build this game on a physics engine that has no idea that this game even exists. And we did that through a bunch of inheritance. We had jumper object, extend that static object, and just added some unique IDs. And then platform and wall inherited jumper object, which by transitivity inherits static object. So we do have 2 static objects of type platform and wall. And we overrode the functionality of collide with dynamic object. In the physics engine code, these methods were only meant for testing. We just had default implementations that remembered the values of the parameters when it's called, just so we could do some testing with those. We don't need testing behavior anymore. The physics engine is all tested. We're confident that it works well. Now we want to replace that with some actual functionality for our game. Landing on platforms and colliding with walls, setting the player's velocity to what it should be, and updating its location, making sure we don't have any clipping here. The only way we'd have clipping here is if we have too slow of an update. If our frames are way too long, we might accidentally clip through one of these. But we want to avoid that as much as we can. So our player class then extended dynamic object, and now it has physics applied to it. It goes completely compatible with our physics engine. Gravity is going to be applied. The velocity is going to be used to update the location. And then our job from this game, and collisions of course, collisions will be detected. Our goal in this game is to set the player's intended velocity. We're going to control the velocity. The physics engine never changed velocity except for gravity in the z direction. But that's our job now, is to set the intended velocity. That's where this player wants to move, and then the physics engine is going to decide if that's valid or not. If the player collides with a platform, a wall, as gravity changes, it's going to change the z velocity, things like that. So we're going to set the intended velocity as these players move around, and then physics takes over from there and decides where the player is actually going to end up, where that location will actually be updated. So how do we change that velocity? Well, we got 3 buttons: left, right, and jump. Either A, D, and W, or the arrows left, right, and up. So as the player is hitting these buttons, we're going to set some intended velocity, and what that velocity is set to and what dimensions and everything is going to be decided by the states. And that's the good stuff. This is what we want to talk about today. Most of what we've just reviewed was just saying how the inheritance and polymorphism was applied to get the physics working. Now we want to talk about the states to decide exactly how we're going to set that velocity, that intended velocity of the player, as the user is hitting these buttons. All right, so we have this spec sheet we need to build, and this is the problem we're facing. We have a spec sheet, we have a bunch of bullet points of functionality, and we have to implement all this in our game. This is the situation you were in for today's lecture question, Friday's lecture question, you were in Monday's lecture question, and for the homework. We have a spec sheet. Where do we go from here? How do we implement all this functionality? So this is where we're going to take that intended approach to, that recommended approach that I mentioned at the end of last lecture, and go through the design process of how we turn this spec sheet into a state diagram and generate all our states in our API and stuff. And yeah, we could do this without states. We could accomplish this unless you're using something that accomplishes the same thing as the state pattern. The code's likely to get messy. It's likely to be hard to maintain, hard to add new features if we don't have some sort of organization. And this week, of course, I'm pitching the state pattern as that solution to organize this code. So how do we do this? I recommend these steps in this order. Start with the API. What are the methods that are going to be called that I'm going to defer to the state? What state should exist? So what situation can my player be in where I'm going to have different sets of behavior from my API methods? And then finally determine what state transitions. How do I transition between these states? What method calls or what events are going to happen where my state is going to change my state? So start with the API. I'm going to look through this. I'm going to parse through the spec sheet and look for any case where the player is being interacted with from the outside world. This is mostly the button presses. I'm going to notice a lot of key presses. When event happens, how long, well, an event kind of, but doesn't use the word when. But a lot of things that can happen, that outside forces that are interacting with my player and making it have different behavior. So mostly those 3 button presses and releases. When jump is released, I'm going to jump higher. When these keys are pressed or released, there's different behavior. So press and release, I got 6 methods from those. And also I have this one kind of oddball one, landing on a platform. Landing on a platform is going to have different behavior based on my state. I'm going to send that to my state for functionality. Arguably, we could probably do this through the physics engine, but there's one thing we need when we are falling and land on a platform. The platform is going to take care of our z velocity and our z location, but we have to trigger the state transition. So we are going to have to know about that so we can transition to the standing state after we land on the platform. So we do have to know about that in this class also. Next, I'm going to look at which states I'll need. So what situations can I be in where my API methods are going to have a different set of behaviors, where I'm going to have at least one of those methods that's going to have a different behavior that's going to be a new state. So if I look through this, I can pick out the words where I feel like it's a different state and come up with those states. If I'm standing, walking, jumping, which we'll call rising, falling, or dead, we're going to have different behavior, different functionality from the API based on these. And I don't see anything else where I'll have a different set of behavior. So I'm feeling good that these are my 5 states, just by parsing through the spec sheet and really thinking about what behavior I want from this player class. And finally, the state transitions. What triggers a state transition in this class? Well, if I'm standing and left or right is pressed, I'm going to transition to the walking state. If I'm walking and I release left or right, transition to standing. If I'm either walking or standing and I jump, I'm going to be jumping. If I'm falling and land on a platform, I'll end up in the standing state. If I'm walking and walk off a platform, importantly, I'm going to transition to the falling state. Jumping and reach the apex of the jump. This is one oddball transition, which we will actually use a conditional for. This one doesn't make a good lecture question or homework, because we will end up using one conditional in this thing. We'll have some if to say if my z velocity is less than 0, meaning I just hit the apex of my jump, transition into the falling state. I couldn't find a way. I don't know if there is a way to do that without a conditional. So it wouldn't make a good lecture question because I can't ban conditionals. And then from any state, if you reach the bottom of the screen, enter that game over state. Yeah, the lecture questions and homework assignments, they're carefully crafted to make sure you don't need a conditional. So nothing like this comes up. Then I have to think of a new way to force the state pattern. Force you to use the state pattern. So with all that, if we process all that, we can draw our state diagram. Highly recommended that you draw your state diagrams for your homeworks, for your lecture questions. If you come to office hours and you don't have a state diagram, it's probably the first thing I'm going to ask you to do. Draw out your state diagram, show me what your program is doing. To get your head around everything that you're designing is very useful to draw these state diagrams. When I was writing my solutions for calculator and microwave, I spent probably most of my time just with a pen and paper drawing state diagrams, drawing things out, making sure I have all the states I need, making sure all the transitions are good. And then once you have this, implementing the code is actually pretty easy with the state pattern. Getting to this point is difficult. We're putting a lot of work on our design at this point. Once you have your design and your state diagram, implementing the code is very little work. You just look at each state and each API method for that state and implement it. So you're asking yourself questions like, when I'm falling and the user hits the left button, what should happen? When I'm walking and somebody hits the jump button, what should happen? Each one of those methods is fairly simple to write because our focus is so narrowed down. In this one state, with this one action, what should be the behavior? So each individual method is easy to write. But getting to this point where you have the state diagram, that's where most of the work is. That's the most of the work. Nobody should be coding for more than maybe an hour or two on calculator and microwave. But to get your state diagram and everything designed, that's going to take the bulk of your time. Or ideally, don't jump into the code. If you jump into the code and I see you in office hours, in the TAC in office hours, you're not just going to brute force this one. You got to design. You got to do a lot of design work first. All right. So any questions about the design of this one, about how we got to this point, or anything like this, or anything about this? Because at this point, it's a matter of doing the coding. The coding should be easy. If your coding is turning into something very difficult, revisit your design is my advice. But at this point, it's going through each state and each API method and implementing those methods. Going through the spec sheet, okay, if I'm in this state and this API method is called, what's that behavior? And code it all up. No questions on this? Okay. So there's something we can flash back from last Monday and take advantage of something that we learned about inheritance. Is we need these 5 classes, these 5 states. And we know they're all going to extend some state class, which is going to be the variable type of the state variable in our player object, in our player class. But we're going to have a lot of common functionality between some of these states. So walking and standing, they're going to share a lot of common functionality. So similar to our health potion and ball example from last Monday, we can factor out that common functionality, extract that into some abstract class, factor that out into some abstract class, and then only write that code once. So we're avoiding a lot of duplicate code. So any state where I'm going to be on the ground, I'm going to implement this on the ground class and have any of the common functionality in that class, and then extend that through standing and walking. So I can have both of those classes just inherit that functionality from on ground, and then only implement the functionality that needs to be different between the two. And then we get all the advantages that we talked about before. If we want to add more on the ground states, if we want a running state, we want a speed running state, we want a ducking state, we can add all those, extend on ground, and then only implement the functionality that's different between all those classes in the concrete classes themselves, instead of extending directly from state and implementing all of that behavior in every one of these classes. Same thing on the other side, rising and falling have a lot of common functionality. Put all that common functionality in air, and extend in air from these classes. All right, let's take a journey through the code and see what this stuff actually looks like. So that's kind of abstract diagrams and just talking about things, which is at this point in your careers, we want to start thinking about more design. Well, let's look at the code too, just to make this a bit more concrete. So here's the player class. I have a little bit of extra functionality. I won't talk too much about the extra stuff. I want to focus on the state pattern, but I got to at least mention them because I'm flashing them on the screen. But I have these variables to store the different speeds and velocities, how fast we'll walk, how high we'll jump. We jump higher just by setting our velocity to a higher value when we hit the jump button. And then the physics engine with gravity takes care of how high we'll actually jump. We're not actually computing how high we'll jump, we're just setting the initial velocity when you hit the jump button and then handling it that way. So I want some constants to store all these values. Then I have these helper methods at the bottom that my state objects are going to call whenever they need to change any of the velocity of this player. If they need to change, if something jump was pressed or anything, I want to call these methods to make those changes, or stop, which is going to zero out the x velocity, and I'll call these methods. When I have this set up this way, if I want to change the behavior of this game, maybe I want a walking jump to be higher. I change that value, and that changes everything in my code for both players, for every state, any state that wants a walking jump. That just changed that everywhere across all those classes. All of those changes just happened. This could be a mess if we have this number hard-coded throughout our code. We got to chase that down. Where do we use that number? Especially if we have magic numbers, which are numbers that are never stored in a variable, aren't labeled or anything. It's hard to tell what they were, what you were thinking when you wrote that. If I have a setup like this, it's really easy to change things. And if this is a game that we're trying to release to the public, we're going to want to spend a lot of time tweaking these variables to get that exact feel of our game that we want. I spent some time tweaking these to get a decent feel for the thing. certain behaviors that I want. I want a full jump to reach the next platform. I don't want a full jump to be like just barely short of a platform, things like that. So I was tweaking a bit, but if we were really releasing this thing, we would spend a lot of time tweaking these variables, maybe adding some new features, adding some more quality of life things. Next, I don't want to talk much about these either. I talked more about the last one than I wanted to anyway. The state, first of all, starting in the standing state. And then I have some extra code to check if the keys are held. Instead of relying on the GUI to send me the events that a key is being held down and handling those, I want some better functionality. The GUI is a little slow sending those messages, sending those events to me. So I want to create those myself and send them on every single frame. So I have some extra logic to check if the keys are being held down. And then I have my API methods, finally. Left press, left, right, jump, released. And I'm just deferring to my state after my held buttons, after I'm doing the actual logic, just to smooth things out and get a better experience with the held stuff. I'm going to defer to my state. And same with on ground and platform collision. This is the colliding with the platform. That's our 7th method that we had in the slides. Then a few extra helper ones. Update, which is going to track how long I've been in a state and also find the apex of my jump. And then is alive, this is just something that I have to be able to print this message here. I just want my game to know that a player reached the bottom of the screen. So I have this extra method just to be able to interact with that player like that. So the state class, again, a little extra logic, mostly keys being held down and finding the apex, the one conditional that I really had to have. These other ones I could probably do without conditionals. But this one I really had to have, checking the apex of the jump and then calling the falling method based on hitting that apex. And falling kind of being like an internal method, not really part of the API, it's just something I need internally to be able to handle that. And then I have the default behavior for each method. I actually did implement every single method in the state class, so technically I don't have to have this as an abstract class, but I still marked it as abstract to make sure nobody's creating new player state objects, because that wouldn't make much sense for our application. But I did give these default behavior of doing nothing, and left released and right released is going to have default behavior of stopping the player, which sets their x velocity to 0. So I have a little bit of default there. Oh, and is alive, default to true. There's only one state cares about that, so let me give it a default behavior so I'm not saying override, return true in all but one class, the game over class, which just nulls out all functionality and returns false. Next, let's look at our on ground. So on ground is going to extend player state, give us the behavior we want. Left and right press is going to change our x velocity, our intended x velocity, and transition to the walking state. And if I walk or fall off a platform, I'm going to transition to the falling state. So potentially we might have a game where you can be standing still and the platform moves out from underneath you. Maybe that can happen. So I'm going to put that in the on-ground state, abstract state. If we're standing, the different behavior we want, we're going to extend on ground and get all that functionality. The one different thing is jump press should use the standing jump velocity, so we should have a smaller jump if we're standing still, then transition to the rising state. If we're walking, the left and right pressed, I didn't have to do this, but I'm overriding that to get rid of the state transition. We're already in the walking state, so we don't need a state transition. But if I add that, keep that state transition in, you can see down here I'm printing out all of the state transitions every time a new state is changed. If I left that state transition, whenever I'm walking, holding down left or right, it's going to say walking, walking, walking. It's going to print that every frame. I just didn't want that, so I overrode these to get rid of that behavior. But this isn't strictly necessary. Jump pressed, I want my walking jump velocity, so I can get my higher jump when I'm walking and jumping, but still transition to the rising state. And if I release left or right, I'm going to transition to the standing state again. Over on the other side, in air, extends player state. And if we change direction, we want to change to our mid-air speed. So we want to have a slower speed after we change direction while we're midair. Once we jump, we're going to be in the rising state. We're going to extend in air. If we hit our apex, we're going to start falling. And if we release jump, we have to have that mechanic where how long you hold the jump button is going to change your jump height. Well, this is it. When we release jump, when we're in the rising state, cut the z velocity in half. Feature complete. One line. So this is where we really start seeing the power of the state pattern. When we're thinking about that feature, okay, when I'm jumping, if I hold it longer or release it, it's going to have different behavior. So where does that fit in my state pattern? Well, that only is applicable when I'm rising. And if I'm rising, I know that the player just hit the jump button. So I know the jump button is down because that's what this state has to have. And then once that jump button is released, that's the only event that relates to that feature. So it's only when I'm rising and when jump is released. And how do I implement that? Well, I'll just cut the z velocity in half, cut that momentum down, and then that player starts falling sooner. So once we have our structure set up, and there's no questions, by the way, of does this line of code break other functionality? If we have these in giant methods, we will have those questions. Can this be called when we don't want it to be? Well, with a state pattern, no, unless we're accidentally in the rising state, or this API method is being called accidentally when it's not actually, that event didn't actually occur. Those are the only two things that can really happen. So as long as our design is solid and our transitions are working fine, there's no question that this functionality is working. It's not some big blob of code that I'm showing you and saying, look, this conditional and this loop, everything's going to work the way we expect it. I don't really have to do much to convince you. When we're rising and jump is released, cut the velocity in half. It has to work. I mean, it doesn't have to, but there's not much that can go wrong there. Then when we transition into falling, we'll get all the in-air functionality. Except when we hit a platform, we want to transition to standing. The platform itself is going to take care of our velocity and our location, but we need to transition to state. We don't want to be standing on a platform and still being in the falling state. We're going to have some really buggy functionality at that point. We want to make sure we're in the correct state, so let's get that state transition. Do we have questions about this? Is there anything, I went pretty quick through it. Is there anything that I went a little too fast you want to see again? Let me explain a little better. Two people on Twitch don't have questions either. No questions? Then as we jump around, I am printing all the state transitions. You can see those. We can see those transitions as they're happening. Which I recommend. If you finish the physics engine, play around with that, change the state diagram, change the things around, see what you can do with that functionality. Okay, if there are no questions, we'll keep on. So what I keep pitching about all this OOP stuff and the state pattern in particular, and polymorphism and inheritance also, what I keep pitching is this is going to make our programs easy to expand. It's easy to add new features as opposed to having massive methods with potentially hundreds of lines of code. This is going to make things a lot easier to expand. You can kind of see that in the code. All those methods, I don't know if we saw a method that was more than 3 lines of code, at least not part of our API and our states. There's a lot of room to expand. You can add a lot more complexity to each one of those without making your code unmanageable. You can reason yourself around every single one of those methods, and as long as your state diagram's working right, your state transitions are working the way you designed it, you can have a lot of complex functionality. You can expand those methods and still wrap your head around them. If you expand each one of those methods to 10 lines and add that much more complexity, you can have a really advanced jumping mechanic in this game and movement mechanic for the player. and still not have your code base be out of control. You could still bring people on and explain, once they know what the state pattern is, okay, in this state, even if they don't really, when the player's standing and this button is pressed, this is what happens. That's fairly easy to reason around after it's designed. Again, the design is the hard part. Getting to that point. So we can easily expand this. I keep pitching that. So let's do exactly that. So let's add a double jump to this game, which of course is already in. But a double jump, for those of you who don't have experience with platformers that have this mechanic, or just aren't familiar with video games, what this means is while I'm in the air, I get one additional jump that I can make. So every time I'm in the air, I have one extra jump press that I can make. And this works well falling off platforms too. If you walk off a platform, the game's going to give you one extra jump. After that jump, so if I jump, use my double jump, now my jump button doesn't do anything anymore. I can press it 1,000 times. If I could push it that many times while I'm in the air, it's not going to have any effect after I use up that double jump. So if I walk off a platform, use my double jump, and then try to use another one, it doesn't do anything. And we can get some pretty good height by taking advantage of this double jump. All right, so how do we add such functionality to this game? Again, with poor design, I feel like I'm saying it too many times. Yeah, with poor design, this could be pretty difficult. Depends on how the design is and what specifically makes it poor. But this could be a tough thing to add if your program is just barely hanging by a thread, just barely together with proverbial duct tape and string. It can be hard to add something if you're writing code and you're like, don't touch it, it's working right now. Don't change anything. I'm sure you've been in that position before. I know I have. You have this code that's just barely working and you don't even know how it works. You try to add a double jump to that kind of code base, that's hard. With our state diagram, with our state pattern, no problem at all. We're going to need a few new states because now we have some functionality, some set of API method implementations that will be different from anything that we have in our current states. So we're going to add a few more states, both rising and falling after a double jump. We're going to add to our rising and falling classes the jump capability, which it was there already, of course, and I'll show that, but I skipped over it when I was talking, when I was showing all that code. Rising and falling will add the jump button is going to set the z velocity to some jump velocity, and then transition to the rising after double jump state, which blanks out the jump button. It just says jump button doesn't do anything anymore. But other than that, does exactly what rising does, and falling does everything that falling does. Rising has one extra change that we'll talk about. We'll see in the code. And not change a whole lot. So we have two new states, but since these states have almost the same functionality as rising and falling, they can just extend rising and falling and just make the change that they need to change to the behavior. We don't have to write a whole new state, whole new states. We just extend these states that these are almost identical to, and then change just what we have to change. Now we could do it like this. We could have the conditional and just say if we've already used our double jump, don't do anything. If we haven't, say that we used it and set the velocity to something. We could do it like this, and arguably for this specific thing, probably a simpler approach. Doesn't really clutter up the code that much. Probably better than having two new classes and two new states. But if your professor says you can't do that, we're going all in on the state pattern with this, with these lecture questions, with these homeworks. Let's do this with states and do it the state way, thinking 100% state pattern all the way. So with this, we add these two new states, add them to our state diagram, which is starting to get a little cluttered, and add in the appropriate state transitions to be able to get these mechanics in our game. So we're going to, when rising and falling, when jump's pressed, we're going to move to this rising after jump state. Apex reached, making sure that rising after double jump goes to falling after double jump, not falling. If we go back to falling, now we got infinite double jumps. We don't want to have a bug like that. We don't want to have that kind of error. Then falling after double jump, if you're hitting a platform, go back to the standing class, to the standing state. rising, so we want mostly the same exact functionality as rising, except we're going to disable that jump button. And when we start falling, we're going to falling after double jump, not falling to prevent that infinite double jump potential bug. If you hit the apex, you start falling, you can jump again, you hit the apex, you start falling, jump again. We don't want that. We're going to go into the falling after double jump state. Falling after a double jump is the same as falling, except we're disabling the jump button. We're just overriding whatever functionality the jump button used to do when you press it. I don't care what it used to do, it's doing nothing now. Which what it used to do was this. We don't want it doing that anymore. Does nothing now. This double jump, carefully crafted. By the way, if you're doing calculator, double jump is just like the decimal button. When you're coding that decimal button, think double jump. That's what I want you to think about. The decimal button, the first time you hit it, has a lot of meaning. That adds a decimal. We're starting the decimal portion of this number. We're going to start building a decimal portion. If you hit it again, if you hit it 100 more times or 1,000 more times, it has no meaning. That button should effectively be disabled. So if you have each state where the decimal button means anything, if you extend those states with some after decimal press state that is the same state just with the decimal button disabled, you can get that decimal functionality by adding those new states. Technically, you don't have to. There are approaches where you don't have to use, where you don't have to have new states for that. I've seen some clever approaches students come up with, some pretty clever stuff. But the intended way, create those new states and just disable the button. It's a lot cleaner, in my opinion at least. A lot more concise. Like, there's no question if you look at that, okay, yeah, that's going to disable the button. There's no logic. If you use another approach, there can be bugs there. It's never clear with all the different logic to use. Find the decimals, find the first one and replace all the decimals after that. Like there are little mistakes that can be made there. By all means, go for it. Go for whatever approach you want. But that's the intended way, is create two new states. I'm leaking a little bit there. I did say this in the other lectures. I don't think I said it here. For my calculator solution, did I say, with 3 lectures, they all blend together at some point. Did I say the thing where whenever you hit a button and some buttons do different things? Did I go through that one? I think I did it at the end of the previous lecture. I'm trying to figure out exactly where. I did not. Okay. So with the calculator and the microwave, when you're starting to design those things, the approach I start with, of course, start with your API, but the API is already defined for you. It's in the calculator microwave classes. So then it's figuring out what states you have. What are the different states based on the different pieces of functionality? And you know you have at least one state. The initial state, when I first create a new microwave or a new calculator, I have some state. And then think about what all the buttons do in that state. Every button is going to have some particular piece of functionality in that initial state. And there are some buttons that you're going to press that are going to change the functionality of at least one of the buttons on the calculator or microwave. So every time you hit a button that's going to change the functionality of any of the buttons, you just hit a state transition, you're in a new state, and now you want to ask yourself, okay, I have this new state, what's all the behavior in this new state? And in that state, you're going to have some buttons, all the buttons will have some specific functionality, and some of the buttons are going to change the functionality of at least one other button. Well, you just hit another state transition there. So each button that you can press that changes functionality, you hit a state transition. What's the functionality in that new state? And the states aren't as concrete as they are in like the lecture questions. The TV can be on, off, or muted. The states are kind of jump out at you by design. That's designed to be an easier question. The microwave and the calculator, there's some internal states that aren't quite as intuitive. So what buttons can you press that are going to change the behavior of any of the buttons? You're asking yourself that and creating your transitions in your state diagram and building out all these states. And then at some point, you're going to have a button that changes the functionality, and you have this state that has identical functionality of a state that you've already written. Well, you just transitioned back to this state, and now you can start closing in your state diagram and start finishing up your design and wrapping things up to be able to complete your state diagram and your design of that. Once you start getting those states that are already existing and you're traveling back to them, get your whole state diagram, Then, and only then, it's time to start actually coding and implementing those states. With my, and I mentioned this in the other 2 lectures, I better mention it here, y'all will be mad at me. My calculator solution, to give you a kind of a rough idea of where you're at, my calculator solution has 6 states in it. And I could cut that down to 4 with the decimal button, if I did those tricks that some students use to get down the decimal button. But my solution has 6 states. If you have significantly more, significantly less than that, you should have an idea that you're off track. Some students do have significantly more if they have some number of states multiplied for each of the 4 functions that you can have. And that's okay if that's your approach. But 6 is definitely feasible. 4 is feasible if you handle the decimal in a special way. Less than 4, I haven't seen it yet. I had a student claim they did it in 3, but they weren't able to show me full functionality. You're going to need at least 4. So just to keep you on this. And the number's similar. I forget off the top of my head how many in the microwave. I think I might have had 7. It might have been 1 more. But it's in the same area. It's in that same range. I tried to keep them somewhat similar difficulty.